All right, let's get right into it. Today, we're building a solid technical foundation for one of Docker's most critical concepts, how it handles data persistence and storage. If you've ever spun up a container, done a bunch of work, and then watched it all vanish, well, this one's for you. So, here's our game plan. We're going to start with the core problem, why containers are so forgetful by nature. Then we'll look under the hood at the Docker daemon, the brains of the operation. After that, we'll unpack the 3 main ways to solve the problem, see how they work with some real-world code, and then wrap it all up with some clear advice on what to use and when. First up, let's talk about the problem itself. Because, to really get why persistence is so important, you first have to understand why data isn't persistent by default in the Docker universe.
This is really the heart of the matter. You run an app, you create a log file, maybe you install a new package, you make changes inside that container. Then you run Docker RM, and poof, it's all gone. So where did it go? The answer is actually baked into the way containers are built.
And this is it, right here, the writable layer. Think of your Docker image as a set of read-only blueprints. When you start a container from that image, Docker slaps this thin, temporary, writable layer on top. Every single change you make, every file created, modified, or deleted lives only in this layer. So, naturally, when the container is destroyed, that layer gets tossed out right along with it, taking all of your data with it. Okay, so how do we get around this problem of the disappearing layer? To do that, we need to peek behind the curtain of Docker's architecture and meet the component that's in charge of all this storage stuff. Meet Dockered, the Docker daemon. This is the engine that's always running in the background. You can think of it as the general manager of your entire Docker setup. When you use the Docker command line, you're not actually doing the work yourself. You're just sending instructions to the daemon. It's the one that handles all the heavy lifting of managing images, networks, containers, and, most importantly for us, storage. And this is how that whole conversation works. You, sitting at your terminal, type a command like docker volume create. That's the client. Your client then wraps that up into a nice API request and sends it over to the daemon. The daemon catches the request and says, got it. Then it goes and does the actual work, carving out a piece of storage on your host machine's file system completely outside of any container. So now that we know who's in charge, the daemon, let's look at the tools it gives us. There are basically 3 main ways to get our important data safely outside of that temporary writable layer. This table really breaks it down beautifully. You've got volumes, which are fully managed by the Docker daemon itself. This is the preferred way to go for production data like databases. Then you have bind mounts. Here, you are in control. You're telling Docker to mount a specific file or folder from your host OS directly into the container. Perfect for development. And finally, there's TMPFs mounts, which aren't for persistence at all. They live entirely in your computer's RAM, which makes them super fast, but also means they disappear the second the container stops. Okay. Theory's great, but the best way to really get these concepts is to see them in action. So let's walk through 2 of the most common scenarios you're going to run into. First up, the classic production scenario. You've got a database chugging along inside a container. It's critical, absolutely critical, that you don't lose that data, even if you need to update, restart, or just completely replace the container it's running in. And this is the command that makes it happen. The magic is right there in the -v flag. What we're saying is, hey, Docker daemon, I need a volume. Go ahead and create one for me called datos SQL, and then I want you to connect it to the /var/lib/mysql directory inside my new container. And that's where MySQL keeps all of its data. So here's the key takeaway. The life cycle of that datos SQL volume is now completely separate from the MediaDB container. You can stop it, remove it, update the MySQL version, and spin up a brand new container. As long as you tell that new container to use the same datos SQL volume, your database will pick up right where it left off, with all its data intact. That is what robust persistence is all about. All right, now let's switch gears from production to development. In this case, our goal isn't long-term data survival, it's all about speed and convenience. We want to edit code on our machine and see those changes reflected inside a running container instantly. The command looks pretty similar, right? But look closely at what's inside the V flag. It's not a simple name anymore. It's a full, absolute path on the host machine. This is what tells Docker, hey, this isn't a volume, this is a bind mount. What this does is create a direct, real-time portal between the host and the container. The app folder inside the container isn't a copy of your files. It is your local project folder. So when you hit save in your code editor, the Nginx server running inside the container sees that change the very instant it happens. This gives you an incredibly fast and powerful development loop, and you don't have to rebuild the image every time you change a line of code. So we've looked at the problem, the architecture that solves it, and the tools in action. Let's pull it all together now and lay out some simple, clear guidelines for choosing the right storage method for whatever you're working on. Honestly, it boils down to a pretty simple decision tree. If it's application data that needs to survive, like in staging or production, use a volume. It's the Docker native way. If you're in development and you just want to link your source code into a container, use a bind mount. And for those special cases where you need blazing fast I/O for temporary sensitive data, TMPFS is the tool for the job. This quote just nails it. It perfectly captures the whole reason this stuff exists. The fact that containers are disposable and lightweight is their biggest advantage, but that advantage means we have to be smart about how we manage the important, stateful data that our apps rely on. And that's our deep dive on Docker storage. So the next time you're crafting a Docker file or a Docker Compose setup, I'll just leave you with this question to think about. Are you choosing the right persistence strategy, not just to get it working, but to make it truly robust, efficient, and secure for your specific use case? Thanks for tuning in.